So I'm going to go a little bit beyond Griffith here. And I want to start our discussion by talking about what happens when I put conductors in an E field. And there are two conditions that basically can happen. One is called static condition, and the other is called dynamic condition. So what does the word static mean? It's where electrons don't flow. And what does the word dynamic mean? When electrons start to flow. So let's start with the static condition. 1, place copper in an external field. Let's say E0. So since we're talking about conductors, I want you to think about a conductor as if it was a gas in which the electrons are free to move. I know it's not, but I want you to think that. So think copper as a gas, in inverted commas, of electrons that are free to move in a lattice of copper ions fixed in place. Will the external E field exert a force on the electrons? And will that force be equal to that? So let's start drawing this. I have copper, a slab. I place it in an external E field. E0. What will happen? Remember, those little electrons are free to move? If this is the direction of the E0, which side is positive? This side? And which side is negative? That side? So what will the electrons do inside this copper slab? Pick a color for electrons. Pick a color.
Blue.
Blue. So these tiny electrons will move up. In response to the E field, the external field that we're applying to it. What will happen? Will there be a excess of electron here? Which means what will be the charge at the bottom? Plus. because of the deficiency that the electrons created, correct? Will this set up another electric field inside the copper slab? What direction will that field be? Up or down? Up. Good, CJ. Suppose I call this field E1. Then I will have two fields, one E0, and they're all vectors, right? And one E1. May I write this as net E E0 minus E1? For this situation? However, did we not know that the E field inside a conductor has to be 0? Yes, we know that. And because of that, what ends up happening is this. Where the E field on the inside has to be 0 in a conductor. Now, what's the use of me going through all of this? Well, this holds true for all objects. And what we can say is, no matter what shape I make my conductor, I know that the E field inside it must be 0. So if I have an external field, say plus here, and minus here, what will the field lines do? This is very interesting. Pick a color for the field lines, right? Purple? Mm-hmm. Okay. What it will do is, far away from the actual conductor, the field lines will be straight. Oh, this doesn't look straight. So the field lines will be straight. But what happens when the conductor itself gets in the path? Something very interesting happens. This side of the conductor will become minus, and this side of the conductor will become plus. And the field lines will be perpendicular to the surface, no matter what the surface looks like. This in itself always fascinates me. Do you see that? There will be always a 90-degree angle between here and here. Do you see it? Between these two lines. So they will twist themselves around the conductor, no matter what shape it is. And on the other side, it'll do the same thing. That actually looks quite nice. So these should go from the plus to the minus. The plus to the minus, from the plus to the minus. And then from the plus to the minus. So this is the static case, when charges don't go anywhere. Got it? And then you have a conductor. Now, what happens if the charges are actually allowed to flow?